Hi there viewers, welcome. My name is Mavis Groning and I'm a student at the University of Johannesburg studying towards my honors degree in geography. I'm sure by now you're aware that here at HPW we're in the quest of answering the question, why is planet Earth habitable? In answering the same question today, we'll be looking at a topic not too hot, not too cold. But before we start on today's talk, let us recap from our last talk. In the previous talk, we've learned about the journey of a lecture theater. We know why there is something rather than nothing. We learned that the Big Bang made hydrogen and helium. However, planet Earth was still not habitable. We needed stars to form heavier elements, and 1 billion years ago, stars formed. Along with their formation, we had heavier elements such as carbon, oxygen, and nitrogen. So the solar system was formed from the debris of an exploding star. So it is safe for us to say that we are made of stars. This is our hierarchy of models, which will be very essential throughout the course. It will help us answer the question, why is planet Earth habitable? Today we're looking at Earth as a bare rock, with using its model to calculate too cold at -18 degrees. So today's talk, we will calculate our model temperature by constructing a hypothesis, testing it using our model of Earth as a bare rock with a given albedo at a given distance away from the sun. We will also revise from our high school physics in terms of conservation of energy, Wien's law, and albedo to mix that all together to calculate our effective temperature. So from our observation in our solar system, Earth is one of the four rocky planets, which is the only planet that is habitable. So Earth falls between two neighboring planets, which are Venus and Mars. So with these three planets up displayed, we're going to be using the Goldilocks and the Three Bears story reference. So here's a graph I drew based on the planet's distance away from the sun. So as you can see, we have Venus, Earth, and Mars. So as you can see here on the y-axis, we have temperature in centigrade, and x-axis we have distance from the sun. So from our observation, we can tell that Venus is too hot, Earth is too, or it's just right, and Mars is too cold. So between the three, we are going to say that Earth is our Goldilocks zone because it's just right. So from all our observations of this graph, we can draw up a hypothesis that says Earth is habitable because it is the right distance from the sun. So to test that, we are going to need real planets and model planets. This will be our model planets. Please take note because they'll be very effective after our calculations. So as we all know, the sun is a primary source of energy. The Earth receives its energy from the sun. So we're going to be moving on to the conservation of energy. We'll have to start by remembering that the energy cannot be created or destroyed. So for a planet at equilibrium, incoming energy is equal to outgoing energy. As you can see here, absorbed energy is equal to emitted energy. So part A for us will be, how much energy does the Earth receive from the sun? And to know this, we'll have to look at the blackbody radiation. So a black body absorbs energy and converts it into heat. So radiation spectrum is dependent on the temperature of the body. So I'm sure you've heard something like, don't wear a black jersey or outfit when it's hot. Why is that? It's because a black clothing absorbs more heat and transfers it into your skin, causing you to feel more hot on the summer's day. So don't wear something that's very dark on a summer's day. So we're going to be looking again at the solar spectrum, which is similar to a black body, right? So the amount the sun emits is called the solar constant. So It is measured in watt per meter square. So what can we say about this? The sun emits hot invisible radiation in a given amount of energy according to its temperature. So as you move away from the sun, its energy is spread over a bigger area. So what can we learn from this? You know, when you and your friends are reading a book next to a light bulb, you receive more energy, hence everything is clear and visible in the right way. So if you and your friends start moving to four corners of the room, you will still receive the energy, but it will be like not as much as it was when you were near. Why is that? It is because the energy has now got spread all over the room. It's not that it's decreasing or something, it's still the same energy, but you're just further away from it. It didn't decrease, it got spread. Keep that in mind. So again, the earth is a sphere, or is it a circle? It is a circle. So hence we have pi r squared. So please take note of this. We have pi r squared. So you can see it orbits around in a circle. So that is why we give it pi r squared. So now we look at albedo. Okay? When we look at albedo, the albedo property of Earth is 0.3. We want to know how much albedo is absorbed. So we're going to subtract 1 on our albedo. So what can we say from now? From now we can say that we have the solar constant on our part of absorbed energy. We have the radius of the Earth. We have albedo, which concludes our part of energy that is absorbed. From now, we have to move on to the energy that is emitted, right? Because we have to complete our emitted part. So we're going to look at Wien's law and Stefan-Boltzmann's law. Wien's law says that the peak of a wavelength is inversely proportional to temperature, and the peak of frequency is directly proportional to temperature. In conjunction to Stefan-Boltzmann's law, which states that the energy irradiated per meter square is proportional to the fourth temperature. What can we take from this? We are going to take a Stefan-Boltzmann constant here to put on our equation on the sides of our emitted energy. Don't worry, we're still developing our equation. We need to realize that the Earth doesn't emit energy from one side. And remember, the Earth is a sphere, therefore it emits from all sides. To the total area, the Earth emits a radius in 4 times more. So that is why I have this beautiful picture, emanation of Earth, which has arrows pointing that Earth receives 4 times more. So the surface of a sphere is 4 pi r squared. So now you know we have all completed our model equation. What do we have from now? We have the absorbed part, we have the solar constant, which is measured in watts per meter squared. We have the radius of the Earth. We have the albedo, which is absorbed, and we have the constant for Stefan-Boltzmann. So our model is complete. So let's see what we have in everything now. So as I've said, we have solar constant pi r squared, the absorbed albedo, the Stefan-Boltzmann constant, and the Earth as a sphere which receives energy 4 times. So now that we have developed our equation, we are trying to arrange it so that we can plug in the numbers. Here is our plug-in temperature, making T the subject to the formula. So now we plug in our numbers. What do we see? We observe that we see Earth as a temperature at minus 18 degrees, making Earth too cold for life. So when we calculate for everything, this is what the results will be. Super wrong. So basically, basically what am I saying now is that the temperature of Earth falls below the x-axis, making it too cold for life. Sounds wrong. It informs us that there is something missing in our model. So based on our hypothesis, this is the real life event that we will have. So I'm so scared. So this can tell us that whatever it is too much of it on Venus and too little on Mars and just enough on Earth. So to draw up our conclusion, the distance from the sun alone is not accountable for the right temperature on Earth. Our model has falsified our initial hypothesis. So how does all that link to South Africa? South Africa is one of the countries, it's the only countries which is sunny and have clear skies, which makes it very, very easy to study the stars for origin. And also because of its dry land area somewhere, it makes it more perfect for the square meter ray which we have in South Africa, which is perfect for astronomy. We also receive rainfall in summer and winter, other than other countries who receive it either on winter or summer. We have two types of ocean currents. We have beaches in Cape Town which are cold, in Durban are warm, in London are just right. So to sum up, we used observations to draw up a hypothesis based on how much sunlight hits the Earth and how much is reflected. So the Earth's average temperature will be freezing according to our own hypothesis. So which means we were wrong. There are other factors that are involved. What are those? I'm also wondering, and you're wondering, I know. You're curious, so it's nice to be curious. So what can you do is find out on our next talk what is missing on our planet or in our model. So thank you for listening to me. If you have any questions or any comments, please drop them on a comment below. Thank you very much for listening to me.